All right, so this lesson is Intro to Quadratics, the objective being that we can identify a quadratic and its parts on a graph. So this is actually really exciting. Quadratics are something that we're going to spend a lot of time learning about this year. It's a main part of your curriculum for secondary 2. So today we're just sort of discovering what a quadratic is and what it looks like. And just sort of establishing some vocab that helps us to talk about quadratics. And like the intro says, there's a lot of relationships in the world that can't be understood just using like linear equations, like lines. Throwing a basketball into a hoop, or the path of a model rocket into the sky and back down, or like sales price and demand models, or the optimal shape of a satellite dish. Like all of those happen to be quadratic relationships that we can better understand using something called a quadratic function, which you have actually seen before, but we have never called them quadratic functions, not yet anyway. So we're just going to investigate a little bit here using this scenario. So your science class launched a model rocket into the air as a class activity, but you had to stay home sick. Your teacher gives you the equation below and tells you that it models the path of the rocket. Time t is in seconds, so that's important. Time t is in seconds, and the height is h of t, meaning that when we plug in something for t, meaning we plug in a second for t, it spits out a height. So as the model rocket is shot up into the air, if we plug in time into the equation, it will give us how high the rocket was at that time. So what we're going to do to figure out the different heights at different times here is to plug in each value of time, each seconds, into this quadratic function. So to make it easier on ourselves, I'm just going to write the equation here. Plus 100 times t plus 6. So notice that I just replaced each of the t's in this equation up here with parentheses so that we can plug stuff in, because that's where we're going to be plugging in the seconds. And I'm lucky because I'm on a digital device here, so I'm going to make use of my tools here and just copy and paste that same function, because what we're doing is we're plugging in different values of time for this equation all the way down to 6 and then 6.3. That might seem weird, but you'll know why I put 6.3 on there in a second. And then what we're going to do is we're going to graph each of those points on the graph and see what shape it gives us. So I will do one, and then I'm going to encourage you to pause me and plug in the rest by yourself so that you can sort of understand how plugging in something works. So this first one, we're plugging in 0, which very promptly, and I want you to do this on a calculator. This is calculator type work here. So just be careful to type it in just as you have it down here, as we have it in the function, into your calculator. But this first one is pretty self-explanatory because we're multiplying by 0 on these first two pieces of the equation, which make them just disappear. So all that we're left with is the 6 at the end, which ends up being our height at 0 seconds. So input, output here. Next we're going to plug in 1. And again, plug this into a calculator. Just type in -16 times 1 squared plus 100 times 1 plus 6. And if you do that, and I would encourage you to do that, you'll get 90. So here's where I'm going to say pause me, plug in the rest of these points, and then double check with the video once you've done it if you're getting the right answers. So for the value of 2, we should get 142. For the value of 3, we should get 162. For the value of 4, we should get 150. For 5, you should have gotten 106. And for 6, whoa, going somewhere else. For 6, we have 30. And for 6.3, you get approximately 0. It's a very small decimal, but it's close to 0. So now what we're going to do, we have points here. We have input over here, input, output, which makes us a single point on a graph. So what we're going to do is we're going to go on the x-axis and find this value and go up on the y-axis to this value. So that first point being 0, 6, notice that my first point on my graph up here is 50. So 0, 6 is real small down here. 20, 30, 40, 50. So each of these lines is 10. So we're going to be like a little bit more than halfway up to the first line there. And that gives us 0, 6. The next point is 1, 90. So we're going to go over to 1, which be careful on this scale. Oh my goodness, I don't know what's happening. Be careful on this scale here. 1 is here. It's right there. So you go over to 1 and up to 90, 50, 60, 70, 80, 90. Right there. And then 2, 142. So we're going to go over to 2 and then up to 142, which is a little bit above 140 on our scale there. And then we're going to go 3, 162, which is here, and up 162 right there. And then 4 up 150. And then 5 up 106. 5 is here, up 106. Oops, not that low. A little bit more than halfway. And 6, 30. And 6.3 is just a little bit, so this line right here is 6.5. So 6.3 is a little bit more than halfway to that one. And so that's where we put our 0, is at 6.3. So we have this lovely shape here, which we will identify in a second. But I want you to think about for a second why this makes sense. So again, we're modeling the path of a model rocket that we shoot up into the sky. And then because gravity is a thing, it comes back down again. And so this shape is actually an exact model. Well, maybe not exact because we're not perfect. But it's a very close model for how that model rocket moves. It goes up into the sky. It sort of pauses a little bit, like the slope becomes shallower there for a second. So like just like when you throw a ball up into the air, there's this like sort of lull at the top where it's just like it's changing from going up to going down again. And then once it's falling quickly. So this makes sense logically. It makes sense that this is how a model rocket might move in the air when you launch it. And again, like this path also can model like throwing a ball. Like if you were to throw a ball to your friend or something, and you threw it really high up into the air. But I want you to notice that the x-axis in this case is time. So even if something is going straight up and straight down, it's not moving like horizontally at all. This would still model that because it's in relationship to time and not to space or position, right? So it's as time moves, it goes up and then back down again. So that's just a thought. So we're going to answer a couple of questions using this graph now that we sort of have a visual of how this model rocket was moving. So the first question is, how long was the rocket in the air? So it starts at 0, that's where we launched it, and then let's highlight here. Starts at 0, time 0, and then it hits the ground again, which is height 0, right? That means it hits the ground at 6.3-ish, pretty close. So the answer to that question will be, it was in the air for 6.3 seconds. Because our measurement of time is in seconds. Next question, how high was the rocket when it was launched? So here's an interesting thing. Notice that our rocket didn't start out at 0, which actually makes sense. If you're shooting a model rocket, usually it has to be like on a table or like something is like holding it up, right? So it just happens to be that this model rocket at 0 seconds was already 6 feet in the air, which means that when we launched it, it was at 6 feet in the air. So it started 6 feet in the air. Doesn't necessarily mean it ended at 6 feet. It ended at the ground, but started at 6 feet high. So it must have been on a table or some sort of like launching mechanism, so it was up a little bit higher. What was the rocket's highest point, and when did it get there? So this is a loaded question here. The highest point, clearly on this this graph, this here is the highest point. So I'm going to use our actual points on the graph or on the table here to figure out, because my graph is not perfect and I can't really tell what that point value is. But I do know that at 3 seconds it was 162 feet in the air, which is pretty close to its highest point. So we're going to use that because that's, from our information, that's as close as we can get. So the highest point was at 162 feet, and when it got there was at 3 seconds. That's how long it took to get to its highest point. 3 seconds. And then how long did it take for the rocket to hit the ground? So this is kind of a repeat question, because how long was the rocket in the air and how long did it take for the rocket to hit the ground are kind of the same question. So again, it was in the air for 6.3 seconds, so it took that long to hit the ground again. 6.3 seconds. Again, we're rounding a little because our math isn't a perfect model. It's a good model, but not a perfect one. So that is a parabola, that is a quadratic. I know I'm using verbiage here that you're not familiar with, but this is a quadratic function. And so what we're going to do on the next page is sort of talk about the anatomy of a parabola. And this right here, it says we call the shape a quadratic makes when graphed a parabola. So a quadratic graph is called a parabola. That's the word I was using before. We will use that word a lot, and sometimes I use it interchangeably with the word quadratic when I'm teaching, and that's because they're often referring to sort of the same idea here. A parabola is this shape specifically, and a quadratic is the graph that makes that shape. So that's just some thoughts for you. And we're going to just talk about some vocabulary and some hopefully familiar concepts from other times you've looked at graphs, but some new ones as well. So we're going to start over here with domain and range, and I realize in your notes this box is super small. I'm lucky again because I'm on a electronic device and I can zoom in really far and right, but if you need more space you can go out of the box. The domain and range is something that we often talk about. Domain with graphs. Remember that domain is the x values and range is the y values of the graph. So for a linear function, the domain and the range are often both negative infinity to positive infinity because the domain, the x values that exist in a linear function are usually from negative infinity to positive infinity. But I want us to look at this graph here. This shape, the x values, let's get my pointer, the x values are this direction and this direction. So the x values that exist on this graph, even though this function looks like it's gonna flatten out here and make like a flat shape eventually and stop going, what direction is that, right? It actually never stops. It goes slower and slower because the slope of that graph gets steeper, but it actually never stops. So it goes forever in both directions, left and right, even though it looks sort of like it'll peter out and stop, which makes the domain of a parabola still negative infinity to positive infinity. And that's always the case. No matter what parabola quadratic you're looking at, it's always going to be negative infinity to positive infinity on the domain. It's useful because then you don't have to like think about it every time, right? It's always going to be that same same domain. I also want to write it a different way. Often you will see domain as like negative infinity is less than x is less than positive infinity. This is often the way that they write it in like math space and in general. All that means is that x is just in between negative infinity and positive infinity, which truly that's not really a boundary, right? It can go anywhere, but it's just a way to write that the x values go from negative infinity to positive infinity. The y values, on the other hand, that's this direction. Notice that it will go forever in one direction, but the other one, it stops right here. Like there is no graph beneath this point. It's like from this line up, there's a graph, but down, there's not. And so the range of a parabola, and I'm trying to make this more broad than just looking at this specific parabola. Oh, I spelled range wrong. The range of a parabola is always connected to its vertex. So this word right here is something that we will learn in just a second, vertex. But the vertex, I will just tell you, is this point down here. And so the range is always connected to where that point lies, right? The lowest or the highest point of the parabola is going to affect the range of a parabola. So that's domain and range. The y-intercept, which is nicely pointed out here, the y-intercept is just, as you might imagine, let me get a different color because I'm feeling colorful, where the parabola, that's that nice shape, crosses, whoops, the y-axis. For a parabola, there is always only one y-intercept. There can't be more than one y-intercept on a parabola, so that's nice. There's always one y-intercept. Other kinds of graphs might have more than that, but not a parabola. The x-intercepts, and this is something that we will spend a lot of time talking about, the x-intercepts of a parabola are extremely important. It's one of like the main features of a parabola. And notice that this parabola that's graphed here has two x-intercepts. And so there actually is a lot of different options here. Like unlike the y-intercept where there's always one, with parabolas, there may be, and I'm sorry that my writing is so, the marker is too thick, but there may be 0, and what I'm going to do here is I'm going to just draw a teeny little picture of what it looks like sort of when there's 1, 2, or 0, because that super helps me. I don't know about you, but if there are no x-intercepts, a parabola, it's just above the x-axis like this, where it never dips below the x-axis. If there's only a single x-intercept, it means that the parabola, oh, I don't need those. it means that the parabola just comes down, touches the x-axis, and then goes back up. So that's totally possible. There's only one point at the very bottom there, and so if you move that one point to be on the x-axis, it'll only have one x-intercept. And also, just like this graph, there might be two. Anytime the parabola is below, like the vertex, this point down here is below the x-axis, there's going to be two x-intercepts. Parabolas, just like our other page, parabolas are also allowed to be upside down, which changes these pictures a little bit, but I am sure you can probably imagine the different scenarios with an upside down parabola. They might just look a little bit different, but you can still put an upside down parabola where it doesn't cross the x-axis, or where it touches only once, or where it touches twice. And we will learn that these are also called, trying to write neater, they're also called sorry, I'm reading my other notes and I couldn't read them. They're also called solutions or zeros, and we start to use these interchangeably pretty quickly, so it's good for you to know that.
Shanti Temporera, can you please come to the front office? Shanti Temporera, please come to the front office and bring your thing. Thank you.
There you go. I don't think that's the first time that there's been an announcement while I'm filming, recording, which is actually pretty amazing. Anyway, so again, with parabolas, there might be 1, 0, or 2 x-intercepts, and they're called solutions and zeros as well. So those are like things that we just use interchangeably pretty quickly. So that's good to be aware of. And now we finally come to our vertex. Like, this is this word, I've had to use it several times because it's super important on a parabola. The vertex is this point down there. So on an upside down parabola, the vertex is at the top, and on a right side up parabola, like this, just like the one that's here, the vertex is on the bottom. So it's just that like maximum or minimum point where the parabola changes direction. The vertex is super helpful when we're trying to graph parabolas, and also for a lot of other things, honestly. Did I already use purple? No, I used pink. Okay, so the vertex is the lowest or highest point on the parabola. Like the point where the bottle rocket is changing directions. We also call this the minimum or the maximum, depending on whether it's on the bottom or on the top. So that's a super important concept. We call that the vertex. The line of symmetry is something interesting as well. Parabolas are symmetrical, left and right. So this line down the middle, you can fold them in half and they'll match. If you were to like physically fold a parabola in half, those two sides would match each other. And that fold line is called the line of symmetry. So just the line where it's symmetrical. I'm going to use green. This line is where the parabola is symmetrical. Pretty self-explanatory. All parabolas have one though. Because of the nature of parabolas, every single one can be folded in half and they match each other. So here's my little picture. There's a dotted line. That one would definitely not match because it's a bad drawing, but you get the idea. So that's called the line of symmetry. Another thing about this one is if you were to write an equation for the line of symmetry, which we actually do eventually, the line of symmetry is a vertical line. So it's not, so if you write an equation y equals like 6, it makes a horizontal line. If you make a line with x equals something, it makes a vertical line. So these are always an x equals situation because the line of symmetry is always a vertical line. So you can write it x equals, and wherever it crosses the x-axis, so this one is a 1, 2, this is an x equals 2 in this specific case, but you can always write the line of symmetry equation super easy like that. It's just x equals something. Yeah. Concavity. So that's a brand new concept that is like also super cool and super important with parabolas. So let's just talk about concavity for a second. And first we're going to talk about concave up. And so concave is like more what we'll say. A concave up parabola, that's a descriptive word. A concave up parabola opens upward. And you might imagine what concave down means just from that. I'm trying to decide what color to use. Blue? Sure. A concave down parabola opens downward. So concave up, it opens up. Concave down, it opens down. It's just instead of using the terms like upside down or something like this, we can use concave up and concave down. Something that helps me remember this is if you draw a concave up parabola, and then you can put little positive eye signs. It looks like a smiley face. So positive meaning concave up, and there's also a sad parabola that has negative eyes. There you go. For concave down. So that positive and negative relationship with concave up and down, we'll learn more about that when we graph parabolas. But positive parabolas are always opening upward, and negative parabolas are opening downwards. So just as like a quick note on that, notice that this graph here that we just graphed is a concave down parabola, and there's a negative in front of this first term. So just a thought, that's sort of that positive negative relationship. There's usually a negative, not usually, there's always a negative if it's concave down. So that's the anatomy of a parabola. Those are some verbs or verbiage that we need to use in order to talk about parabolas. The important ones, concave up and concave down, are ways to describe whether it's opening up or down. A vertex is that like minimum or maximum point where it changes directions. The x-intercepts, also called solutions or zeros, or where it crosses the x-axis, could be 1, 0, or 2. Y-intercept, there's always 1. And domain and range, domain is always negative infinity to positive infinity, and the range is always connected to the vertex, or that lowest or highest point. So algebraically, a quadratic is any polynomial with a degree of 2. So I would just remind you that the degree of a polynomial from last lesson is the highest power that the polynomial has. So any polynomial that has the highest power of 2 is a quadratic. This is how we'll mostly see quadratics. It will have like an x squared, an x, and then a constant at the end. A, B, and C are just standing in place of normal numbers. That's the form that we usually see them. And we'll talk about forms of quadratics next time, like different ways that they can look and why each are useful, but this is probably the most common. notice that the highest power here is 2, which is what means that's the defining feature of a parabola. So super quickly, down here we're just sort of identifying degrees of quadratics. So for this first one, I should say that again. We're identifying degrees of polynomials and deciding whether or not they're quadratics. So only the ones with degree 2 will be quadratics. This first one is a multiplying two binomials situation. And if you can like sort of look through the math forward into what it would look like, you would notice that we would eventually have to multiply x times x, which would give us an x squared, which means that this degree is 2, and yes, it's a quadratic. This one here also has an x to the power of, I should use my pointer, an x to the power of 2. So that's also a degree 2 quadratic, and yes, it's a quadratic. This one, notice that we would have to, if we were to distribute, we would have to multiply this x squared by the x here, by another x, which would give us a power of 3. So that degree would be 3, and therefore it's not a quadratic. It's too high of a degree there. This one, we would multiply 3x by 2x, giving us a 6x squared, and that's the highest power of x we would get in that multiplication, so that's also quadratic. Sorry if I'm going too fast on this. You're welcome to pause me and see if you can figure out the rest. But otherwise I'm going to keep going. So on this one we have a power of 2 here, but it's written improperly because there's actually a power of 3 in the middle of the function. Which means that it is not a quadratic because it has a degree of 3, and therefore, no, it's not a quadratic. This one is like super easy. It's just x squared, so degree 2, yes, it's quadratic. In this binomial down here, we would eventually have to multiply x squared times x. Same situation as before. That would give us a power of 3, and therefore it's not a quadratic. So this one down here, the last one, is we have a bunch of x squareds, but we would end up just having to combine like terms for all 3 of those, and we would end up with just an x squared as the highest power still. So that is a degree of 2, and yes, it's a quadratic. So that's what we're looking at here. Quadratics always have a power or a degree of 2, meaning that the highest power that they have is 2. And so often they will look like this, and we'll explore more different forms next time. But they, like you see down here, they can look all sorts of different ways before we do some distribution and some math to get them to look like this. They could look like, like this. There you go. So they could look like 2 binomials multiplied together. They could look like this with a distribution happening. They could look like this with nothing except for an x squared, or they could look like this convoluted thing where we haven't combined like terms yet for all of those. So they can look really different, but the defining feature is that they have a degree of 2, which we can always figure out by doing a little bit of distribution or just sort of investigation there. So that's the lesson for today. That's our introduction to quadratics. Next time we'll talk more about what they look like and what each form is useful for. Quadratics are really super cool, so I'm excited to get